Hi girls, so tomorrow we're going to be learning about definite integrals, which are used to calculate the area under a curve, and I want to give you a brief introduction as to how that works. So let's say that I had some function fx that looks like this, just for the sake of having something, and I want to know the area under that curve between A and B, for example. Now, we've seen using the trapezoidal rule and other rules that we kind of know how to do this roughly. And that's exactly what we're doing here. We're saying, how can I do it roughly, and then how can I make that rough guess as close as possible? So what I do is I pick any value of x, so let's just say I pick this one here, and I draw a rectangle, like so. And the rectangle has the same y-coordinate as fx. Right, so this here is fx. And then I draw quite a skinny rectangle, and I said that the x-coordinate of this point is x plus delta x. So in other words, this red length here is delta x. And what I'm going to do is I'm going to do that for every value of x where it fits. And I'm going to add them all up. So let's look at what that looks like algebraically. So algebraically it looks like this, that the area under the curve, which is actually going to be a type of integral, equals the sum of all these things where I'm looking at the area of this rectangle here. Right? So the height is fx, and the width is delta x. Now this symbol here that we've kind of talked about a couple of times in class just means I sum all these values up, and it means when I add this in that I sum them up starting at x equals a to x equals b. Now what I want to do is I want to make this rectangle here as skinny as possible, right? Because if you look really closely, like, if I just draw another little bit of curve down here, and then I draw some rectangles on it, right? So if my rectangles have a pretty long width like so, then all this area here goes to waste, and I don't account for it. So if I draw them, say, half the width or a third of the width, let's say, then all of a sudden the area that's not getting counted is just these little small sections here, and it's much smaller. And if I make them even smaller again, it's going to get very crowded very quickly. But the amount of area that I miss is even smaller again. So what I want to do is I want to make those widths as small as possible. So what I do is I take the limit as delta x approaches 0 of this sum. And it turns out that in like the 1670s or something, Leibniz and Newton at the same time proved that this was actually the integral from x equals a to x equals b of fx dx. And I'll explain what those changes are tomorrow, but basically it's the difference between having a value and not having a value, right? Delta x has a distinct value. It has a width, right? It's not 0. It might be 1 on 10,000. dx doesn't really have a value anymore. It's a limit. It's a function, as it were. But it turns out it doesn't really matter. You can be very successful in this subject without really caring what it means and just actually doing this stuff. So let me show an example of how a calculation looks like. So let's say I wanted to find the area underneath y equals x cubed from x equals 0 to x equals 4. Now I just made that up randomly, right? So, not really randomly, but anyway. So I draw some curve that looks something like this. I've got a line here at x equals 4. It turns out that the area equals this integral from 0 to 4 fx dx, where fx equals x cubed I do the integral, and what this notation means, and again, I'm not really going to prove this part of it to you, but what it means, oh sorry, that shouldn't be b, that should be 4, and that can be a 0 down there. So what it means is instead of writing x, you first of all write 4, so I go 4 to the power of 4, divided by 4, and then you subtract, instead of writing x, you write 0. So that equals 4 cubed units squared, so 64 units squared, and you're done. And that's what we're going to do tomorrow. Now, again, I'll prove all that stuff to you again tomorrow. I mean, as good a proof as you get. But I just want you to see it for tomorrow and have a little bit of a think about some other things that might happen for different kinds of questions. And hopefully you'll come to me with some questions tomorrow. Okay, and I'll see you tomorrow morning. I think, yes, tomorrow morning.